to this point, we've been able to take a definite integral and evaluate the area underneath the curve exactly because all the functions we were dealing with created some sort of geometric shape that we had an area for. We had an area formula to calculate the exact area under that curve. So if we're given a shape or a curve that it does not fall into one of those geometric patterns, we're going to use something called a Riemann sum in order to evaluate or approximate an area under the curve. So this is not going to be an exact area under the curve, but rather an approximation. And this really works well for when we don't actually have a function given to us like an f of x, but maybe we just have a specific set of data about the function, and we can use that to estimate some area under the curve. So it breaks down into three different types of Riemann sums: the left Riemann sum, the right Riemann sum, and the midpoint Riemann sum. All of these are going to still be rectangles, and the base of your rectangle is going to be along the x-axis, and it's going to be a different in x values. So all of them are going to use, your delta x for your width. But in terms of determining your height of your function, or the height of the area that we're going to be taking, we're going to have to take a look at which one of the function values we're going to use. For a left Riemann sum, we're going to use the lower limit, or the lower of the two x values, to evaluate what the height of the rectangle should be. So this might be the first rectangle Riemann sum that we take for that particular drawing. For the next one, we would again focus on the left side of the function value of our rectangle, and that might be the rectangle area we take next. And then for a third one, maybe we take this one right here. For the fourth one, we'd go all the way up to where that function value is. And let's say for one final one, we start all the way up here and go all the way across. So that might be an example of a left Riemann sum. The delta x in this case, or basically how what your base of each rectangle, does not necessarily have to be the same delta x all the way through for each rectangle. However, you are always using the left side or the lower of your two x values to evaluate what the height of that rectangle should be. The right Riemann sum is the same idea, but instead of using the left side of the rectangle, we're going to use the right side of the rectangle to evaluate how tall the rectangle should be. Again, the delta x in this case does not have to be the same. They can be different widths for each one of these rectangles, but the height of each rectangle comes from the larger of the two x values that are evaluated in your function. The midpoint Riemann sum is also a difference in x values for your base, but typically for the Riemann sum, they will be an equal distance because we need to use a middle x value to evaluate what the height of this function is going to be. So we're going to do our best to kind of split up this into equal measurements for a moment. Okay, so there's our best estimate if we were breaking this down into four rectangles of equal width along the base of our x-axis. To determine the height, we're going to go into the middle of each particular rectangle base and use the middle x value to determine what the height of that rectangle is going to be. So as you can see, a lot of these rectangles may overlap or underlap the area that it is given, or the area we're trying to approximate here, based on kind of how the function moves and curves, and you'll see an analysis of when that might be over or under in just a moment. Right now, we're going to just actually use some data to actually calculate or approximate the area underneath the curve. So in this first example, we are given a table of 5 different points. And what we're going to be doing is finding an approximation of the integral from 2 to 13 of our function f of x. And we're going to use both a left Riemann sum and a right Riemann sum to do it. So they also specify which intervals we're supposed to be using. So these intervals from 2 to 3, 3 to 5, 5 to 8, and 8 to 13 gives us the different bases that we're going to be using for our rectangles. So in this case, our base right here is going to be a 1, or basically our delta x would be a 1. Here it would be a 2, here would be a 3, and then across here would be 5. So for each one of these Riemann sums, we're going to be using those same base measurements, but we'll be using different height measurements. So for the left Riemann sum, we're going to have a base of 1 times a different height, a base of 2 times a different height, a base of 3 times a different height, and a base of 5 times a different height. The right Riemann sum will be the same thing. Now, when determining the height, we either use the left x value or the right x value to refer to your y value. So for the left Riemann sum, our first rectangle, we're going to be using the left measurement of 2, and f of 2 would be worth 6. So that is the height of our function. And then we're going to keep going using the left side of each rectangle. But for the right Riemann sum, we're going to end up using the right-hand values. So for this first rectangle, we're actually going to focus on x equals 3 and see that its height was at negative 2. Now, these are approximations. So what we're going to do is when we describe what we're trying to evaluate, and we're saying we're using the integral from 2 until 13 of f of x dx, we're going to use the approximation symbol to represent the fact that we understand that this is not going to be an exact area under the curve, but rather just an approximation of what the area is going to be. You may also see in some textbooks referring to the approximation as either a capital L or capital R, referring to left and right. And sometimes they'll even go as far as to include a little subscript of 4. And in this particular problem, that 4 would refer to the fact that there are 4 rectangles that we are evaluating. So if you were going to do a 10 rectangle left Riemann sum, you might see something that says L sub 10. But we're going to go through, we're going to do some arithmetic and figure out what the actual approximation of this area is going to be. Our left Riemann sum ended up with a sum of 14. The right Riemann sum ends up with a sum of 50. So as you can see, there is quite a bit of a difference between these two approximations. We also have the midpoint Riemann sum that goes after the same idea. Typically, we need a little bit more data to go along with this because we need to have the ends of our rectangle where the rectangle starts and stops, but we also need a value in the exact middle. So in this particular case, we're going to use a midpoint Riemann sum of 3 equal subintervals to approximate what the value is of from 0 to 12 of f of x dx. And the 3 equal subintervals for a midpoint Riemann sum, in some textbooks you might see a capital M with a subscript of 3 to represent the fact that we're using 3 equal subintervals here. So if we're going from 0 to 12, that's a total span of 12 across the domain, divided up into 3 equal subintervals means that each rectangle has to have a width of 4. So our first rectangle is going to go from 0 to 4, the next one will go from 4 to 8, and the last one will go from 4 to 12. But they all have a base worth of 4. So we're going to have our base of 4 times a height, another base of 4 times a height, and another base of 4 times a height. And again, we're approximating the area under the curve from 0 to 12 of f of x. So what we're going to pick for the height is we're going to use the value that's in the middle to determine what the height should be. So since 2 is in the middle of 0 and 4, f of 2 is worth 5. 6 is in the middle of our second rectangle. It has a value of 7. And then 10 would be in the center of our last rectangle, and its value would be 6. So our final approximation would be 72. We have one other type of Riemann sum that is called a trapezoidal sum. And instead of creating rectangles that are kind of horizontal across the top and might have a lot of overlap or underlap, the trapezoidal sum creates a trapezoid instead of a rectangle. So just as a reminder, the area for a trapezoid is 1/2 base 1 plus base 2 times the height. So in this case, when we draw in a trapezoid, we're going to draw in 3 trapezoids here. So here is our trapezoid kind of base structure. But what we're going to do is we're going to end up having a diagonal along the side that kind of hugs the function a little bit more closely than a rectangle would. With a trapezoid, your bases are the sides that are parallel. So in this case, your y values would be the base 1 and base 2, and the height of your rectangle would actually be the difference in your x values, your delta x. So in this case down here, we're going to approximate the value from 3 to 12, the integral from 3 to 12 of f of x dx using a trapezoidal sum. So we've got basically 1, 2, 3, 4 pieces of, or 4 sets of data. So we're going to break this into 4 different trapezoids. So each one of those trapezoids is going to have a 1/2 base 1 plus base 2 times a height. Now, the height in this case is the difference in your x values. So if I look at that really quickly, it's a difference of 2, a difference of 1, a difference of 4, and a difference of 2. Sometimes with the trapezoidal rule, you're going to notice that all of those difference in x values are the same, and you can almost like factor all of that out. That doesn't seem to be the case here. So we're just going to set up each one of these 4 trapezoids kind of on their own and then kind of go from there with the numbers to see what we can do. So the very first trapezoid, we're going to have 1/2. The base values are going to be the y values, the various heights that we have in here. So 2 plus 6. Your height is the difference in x values, which is a 2. To that, we're going to add the next set of y values added together times the height of 1. The next set would be 3 and 5 as your bases, a height of 4. And then we're going to have 5 plus 4 as the last 2 bases times the height of 2. Now, what you will notice is they do all have that 1/2. So if you want to prefer and factor out that 1/2 temporarily while you're doing your analysis or your work, you can certainly do that to make your work a little easier. So it looks like my approximation is a 75/2. So we're just going to make sure, especially if this is a free response question, that we're just going to write down that analysis from the integral from 3 to 12 of f of x dx would be approximated by 75/2.